In the 1960s, at the height of the space race, engineers faced a daunting challenge: how to build a computer capable of guiding astronauts to the moon using technology that, by modern standards, was extraordinarily limited. The solution they devised for the Apollo program was both ingenious and unconventional: core rope memory, often simply called rope memory. This technology did not merely store software, it physically embodied it. Programs were literally woven into hardware, transforming code into tangible, durable structure that helped make one of humanity's greatest achievements possible. Hello, everyone. Giant Stonehead here. If you enjoy obscure science and forgotten history, please feel free to like, comment, and subscribe, and stay till the end for the dad joke of the week. At the heart of every Apollo spacecraft was the Apollo Guidance Computer, AGC, pioneering digital system responsible for navigation and control. Despite the groundbreaking role, the AGC operated under extreme constraints. It contained only about 2,048 words of erasable memory and 36,864 words of fixed memory. The latter was implemented using rope memory. In total, this amounted to roughly 72 kilobytes of read-only memory, a minuscule capacity compared to even the simplest modern devices. Yet this limited memory had to store all critical information required for lunar navigation, descent, ascent, and rendezvous. As memory is so scarce and expensive, engineers could not afford inefficiency. Every instruction had to be carefully optimized, and every bit of storage had to be reliable. This necessity drove the development of rope memory, a system that prioritized durability and precision over flexibility. Rope memory is a form of read-only memory, ROM, in which data is encoded by physically threading wires through or around magnetic cores. Unlike conventional memory, where data is stored electronically, rope memory stores information structurally. Each magnetic core, tiny rings made of ferrite, act as passive component. The presence or absence of a wire passing through a core determines whether it's represented a binary 1 or 0. A wire threaded through a core represented a 1, and a wire bypassing a core represented a 0. When the system was activated, electrical signals passing through the wires induced voltages in the cores, allowing the stored data to be read. The cores themselves did not change state. Instead, they acted as transformers that helped detect the wiring pattern. This design made rope memory fundamentally different from magnetic core memory used for RAM, where data could be rewritten by changing magnetic polarity. Rope memory, by contrast, was non-erasable. Once woven, the program was permanent. One of the most remarkable aspects of rope memory is that it blurred the distinction between software and hardware. In modern computing, software is abstract and easily modified. In the Apollo era, however, the software embedded in rope memory was literally hardwired into the machine. As described by IEEE Spectrum, a rope memory served as the AGC's fixed memory, containing the essential navigation and guidance programs that enabled the moon landing. This approach has significant advantages. Reliability. The physical wiring made memory highly resistant to errors, including those caused by radiation, ever a problem in space travel. Stability. Programs could not be accidentally altered or corrupted. And efficiency. The system was compact and energy efficient, ideal for spacecraft. However, it also had a major drawback, which is somewhat ironic given that it's made of rope. It isn't flexible. Any change to the software required physically reweaving the memory modules, a time-consuming and labor-intensive process. The creation of rope memory was a meticulous process that combined engineering precision with skilled manual labor. Once programmers at the MIT Instrumentation Laboratory finalized the software, the instructions were translated into wiring patterns. These patterns were then physically woven into memory modules. The work was largely carried out by women in factories, often referred to informally as little old ladies by engineers, a nickname that reflected both the demographic of the workforce and the delicate, textile-like nature of the task. Using fine wires and magnetic cores, workers threaded each wire according to detailed diagrams. The process resembled weaving or embroidery, requiring exceptional accuracy. A single mistake could render an entire module unusable. One module could contain thousands of cores and extensive lengths of wire, sometimes totaling hundreds of meters. Because the memory was read-only, quality control was critical. Errors could not be corrected after fabrication. Although rote memory's total capacity is small by modern standards, it was remarkably dense for its time. It could store significantly more data per unit volume than any other memory technologies available in the 60s. Pictured here is Margaret Hamilton, who with her MIT team produced much of the software used in the Apollo missions. The agency's rote memory stored tens of thousands of words of program instructions, including guidance algorithms, navigation calculations, control routines for spacecraft systems. Despite its limited size, this memory is sufficient to support complex operations such as the lunar landing. It was achieved through highly efficient programming and careful prioritization of essential functions. Space is an unforgiving environment, with extreme temperatures and vacuum conditions and high levels of radiation. Any failure in the guidance computer would have had catastrophic consequences. Rote memory's physical design made it exceptionally robust. It was non-volatile, meaning it retained data without power. It was resistant to radiation-induced errors, which could disrupt electronic memory, and the lack of moving parts in simple structures reduced the risk of mechanical failure. These qualities made rote memory ideally suited to the Apollo missions, where reliability was paramount. Rote memory played a central role in every Apollo mission. It stored software that guided spacecraft from Earth orbit to lunar orbit, enabling precise landings and ensured safe returns. Included during the famous Apollo 11 mission in 1969, the AGC and its rote memory handled critical tasks such as calculating trajectories, monitoring spacecraft systems, and assisting with the lunar module's descent. Even during unexpected events such as the 1201 and 1202 program alarms during the lunar landing, the AGC software proved resilient. Its ability to prioritize tasks and recover from overload conditions was a testament to the careful design of both software and the underlying memory system. While rote memory was highly effective, it came with inherent limitations. It was immutable, couldn't change the programs after fabrication. It was very labor-intensive to produce, requiring skilled manual labor, and it had long development cycles because any modification required a ground-up rebuilding of memory modules. These constraints forced engineers to adopt rigorous testing and validation procedures before committing software to rote memory. The result was a level of software reliability that was unprecedented for its day. Rote memory represents a unique moment in the history of computing, a transitional phase between early hardware-centric systems and modern software-driven architectures. Its legacy includes demonstrating the feasibility of embedded systems for critical applications, influencing the development of read-only memory technologies, highlighting the importance of software reliability in mission-critical systems. Perhaps the most importantly, rote memory illustrates how innovation often rises from constraints. Faced with severe limitations in memory and processing power, Apollo engineers created a solution that was both elegant and effective. Core rote memory was more than just a technical solution. It was a profound reimagining of how software could be stored and executed. By weaving code directly into hardware, Apollo engineers created a system that was robust enough to withstand harsh conditions of space and precise enough to guide astronauts to the moon. Though primitive by today's standards, rote memory embodies a level of ingenuity and craftsmanship that remains inspiring. It stands as a reminder that groundbreaking achievements do not always depend on abundant resources, but on a creative problem solving and meticulous execution. In the story of the Apollo missions, rote memory is a quiet yet essential hero, a woven foundation upon which one of humanity's greatest triumphs was built. But what do you think? Were you aware of this storage medium? Have you ever watched a rocket launch? Are you as fascinated with the Apollo program as I am? Feel free to like, comment, share, and subscribe. I'll be posting here weekly. If there's anything you'd like me to cover next, let me know. And now, for the dad joke of the week. NASA is working on their next big project, a spacecraft they will send to the aliens to say that humanity is sorry for making a mess of planet Earth. They're calling it the Apollo G. Till next time, thanks so much for watching.